Well, it's a genuine pleasure to be here. I really appreciate the opportunity. I submitted an abstract, which I thought might be a poster, so it's really fun to be able to speak and tell stories. That's a little easier than in a poster setting. And in particular, it's a real pleasure to follow Jenny, who's one of my personal heroes. So that was, of course, a wonderful talk, Jenny. Thank you so much. These are going to be my personal reflections from people I know that within our collective living memory are talking about things. So I can't go back to 1912, but I'll start more or less in the 1950s and skim very quickly over all these amazing developments in both hardware and software, because that was really fundamental to the evolution of the instrumentation. And try to move through these different changes in the instrumentation and show their influence on the size of chemical crystallography structures, time per structure, and the total structures published in the Cambridge Structural Database. So, starting in the 1950s, clearly we have film methods, obviously dating back to the discovery of X-rays. So we've got film methods, but using quite complicated and elegant Weissenberg and precession cameras. Here's a picture in the Nonius factory of assembly of those cameras around about 1970, but the manufacture of Nonius began in 1948, so that's kind of fun. But if you got the film, what did you do with it? Well, certainly within the memory of many people here, you had to measure the film by eye. So you had graduated film with spot judgers, who were typically young women employed to do this, I understand, and then later auto-densitometers. A few large mainframe computers were starting to come into being, the National Bureau of Standards computers and an early IBM, and programs were starting to be written for those mainframes. And Jenny, this was so neat that you mentioned the true blood calculations, because I own one of these modules of SWAC. Bob Sparks was a true blood student and worked on programming SWAC. In fact, he told me it was about 20 minutes mean time between failure of the tubes. And so you would be running the computer, literally replacing the tubes while you were doing overnight runs. So here's an actual module of SWAC that I had at the office, and I took a picture of it last week because I thought it would be fun to look at. And indeed, this was one of the modules of that exact SWAC that was, as Jenny said, going back and forth with Ken Trueblood, doing the calculations on vitamin B12. So we can touch this. That's where it did those calculations. Really fun. The size of structures was typically less than 30 atoms, mostly inorganic or organic with heavy atoms, and probably took a good year or more to solve one structure, and thus less than 500 structures published by the end of the decade. Now we're coming into the 60s, where there were tremendous developments in instrumentation. The film methods were giving way to the scintillation counter diffractometers, and I'll show you some pictures of these in the next slides. Large mainframes were starting to come in, and most notably, the Oak Ridge programs and the compilation by Jim Stewart of what became the X-ray packages. I think many of us were first using orphals by Busey and Levy and Orphy, and of course, Carol Johnson's famous Ortem. And this is a picture I snapped of Carol at the Knoxville meeting. So it's great to have him back in the field with us. At IUCR Stony Brook in 1969, I think this was kind of a watershed time, people told me, there were at least 9 diffractometers shown in the commercial exhibit. And if you actually look at these, there were more than 9, so I'm not sure where that number came from. But it ranged, and I put them in alphabetic order, ranging from the Datex controlled GE down to the newly introduced Syntax. And according to Bob Sparks, who gave a talk at Eric Buffel's birthday fest at STOA, these were the introduction dates that Bob had taken pains to gather from the various manufacturers still around at that time. So I think that's a neat sort of area of what was going on. The Eulerian cradle, by the way, the name came from Dave Parker, who sensed that the proposed coordinate system for the picker was the ancient set of Euler's angles. So that was an interesting tidbit. So here's what the instruments look like. Here's the Hilbert Watts. These are in alphabetic order. Apparently a huge machine from what people were telling me indeed last night. A weighty piece of metal and very precise. This is what the early CAD 3 looked like, which was in the exhibit at Stony Brook, and a prototype of what became the CAD 4 a few years later, controlled by a PDPA. This CAD 3 was actually in Frank von Meur's lab at Delft. That's where that photo came from. The Dutch Philips PW1100. I don't have a picture of the pale red, and it would be nice to have that from Norelco. And then here's the picture from a recent ACA newsletter in the article written by Bill Busing, talking about the automation that Oak Ridge did of the early pickers. And here it was controlled by a PP5. This was my first diffractometer that I used when I came to University of Toronto. The AFC2 from Rigaku, and thanks to them for allowing us to use the image. Very interesting, I thought. I didn't realize it went back to a 2. I also presumed there must have been a 1. That's really interesting.
Don't assume.
Then there was a quarter pi circle diffractometer designed at the Max Planck Institute in Munich and commercialized by Siemens as the AED series. And the Stoa, which already was a Stadi 4 by 1970, Stoa Automated Diffractometer -4 circle is what that stood for. And my friend Eric Wuffel, who was the director of Stoa for many, many years. And not least, because in alphabetic it happened to come last, the Syntex P1 bar. And that's when I joined the company towards the tail end of the P1 bar days. So I did actually use this, and I did certainly support a lot of software improvements on that as it was morphing into the P21. Here was a wonderful early ad of Bob Sparks with the slant encoder first generation of P1 bars. You would hardly recognize Bob without his beard. And Sten Sampson from Southern California was absolutely fundamental in the mechanical design of the P1 bar. And here was a neat photo of Sten most recently at the Los Angeles ACA meeting. So in the 60s, now we're up to 100 non-hydrogen atoms, getting the structure time down, still difficult, and 8,000 structures already in the Cambridge database. Into the 70s, we have a lot of now routine use of computerized diffractometers in North America, and this is really what I'm focusing on here. In North America, really, it was the Syntex and Enroth machines that were widely distributed commercially, and low-temp devices were gaining in routine use. Here was the rotating glass-linked LG1, which was designed in collaboration with Håkan Hopa. And here's a wonderful picture of Håkan at the Kyoto meeting in '72 when these were introduced. And software packages coming into routine use, the public domain, X-ray, Multan, lot of influence from their many workshops in future development. The early crystals came in at that point. The brothers and Rowlett, I learned from David Watkin, and the first shellacs from George Shelter. And commercial software was introduced in this decade. And indeed, this was something really important that Bob Sparks instilled in all of us, that at every ACA or IUCR meeting, we needed to introduce something new. And so there were milestones in particular in the software development in 1970, which happened to be the first ACA meeting I ever attended. Bob Sparks introduced auto-indexing, and I heard that talk. It was a miracle because I was not yet associated with the company. So I think I decided at that moment that this is where I wanted to be. In 1972, the full range of the automated P21, the densitometer, and the LT1 were introduced and then widely used. And in 1973, we introduced the XTL, which was a complete structure solution, refinement, and display with indeed a custom floating point processor, because those were not widely available in order to make least squares at a reasonable time. We also commercialized a red-green TV display, not too long before they became widely available from places like Tektronix. And this was done in collaboration with Edgar Meyer at A&M. And the first Shell XTL proprietary release right at the end of the decade, which led to a wonderful long-term relationship with George. In the 70s, I think all of these developments were coinciding with the development of computing and of people. So the P21 facilitated, I think, some immensely productive research groups, including the Strushkoff group in particular at ENIOS. I remember Bob telling me that this was really the most productive group in the world at one time. And this was a reunion of the many members of the Strushkoff group that are now in North America. It was a picture of Yuri. And not least, the fact that staff crystallographers started at that time, the first one of which is our co-chair, Kurt, at Colorado. And I did want to mention notable early users, including Bruce. Bruce Foxman, we had a wonderful transaction symposium yesterday, and he was the #2 user of P21 from this users list that I still have today. So hallelujah for all of these early wonderful pioneers. So up to 200 non-hydrogen atoms, structure of time getting down, maybe more reasonable, over 30,000 structures by the end of the decade. In the 80s, we're moving rapidly ahead. More different models of diffractometers, Rigaku, becoming more widely used in North America, though it was always prevalent in Japan. And two-dimensional detectors developed primarily for protein crystallography were being seized upon by the ever-inventive chemical crystallographers to use for their most difficult problems. And I'll show you pictures of those in a moment. PCs were just starting to come in, and more public domain software packages, NRC VAX. Here's a picture of Eric Gay with his paper, and I was lucky enough to work with Eric before I came to Syntex. So I did a little bit of very early work on what originally, in the end, became NRC VAX. And crystals became the child and I'm sure genuine love of David Watkin to this day. And commercial software, Shell XTL, Hexagon package in particular from MSC. Oop, come back. So here's what these early two-dimensional area detectors look like. Ron Hamlin gave me a picture of the Mark I from ADSC before it actually, I think, probably was introduced commercially with Zoom and Hamlin. Here's the FAST from NRAF known as the Uli Arndt inventions. And this was quite widely used for small molecule work. Certainly Bob Scheid at Notre Dame had one of these, others. And here was the Zentronics detector, which became part of our company in the Nicolay days, and Ron Burns, the inventor of that, showing at the McMaster meeting in '86. By the end of the 80s, we're up to 400 non-hydrogen atoms, and I remember being able to do those in the least squares refinement, 1 or 2 weeks per structure, and almost 100,000 structures in the database. By the 90s, people were really trying to push for smaller crystals, weakly diffracting crystals, and typically using the point detector diffractometers in the chemical world, but putting them on rotating anode sources, moly or copper. The first multi-layer Goebbels mirrors were brought out by Herb Goebbels, our director of research at Siemens, and I think notably for our company, the first commercial CCD system was introduced in '93. Many more PCs, public domain packages, Platon with Tom Speck here, and Jacobazzo's package with Sear, and Shell XTL, Naxos, and Texan coming along with the machines. So here was what the first CCD machine looked like for home lab use. We introduced that. Come back. In '93 at a Pittsburgh diffraction conference, and here it is with the classic, now classic fixed chi magic angle. And what was interesting, of course, at the time, we had designed it to collect faster data because we thought people, especially with air-sensitive compounds or otherwise decaying crystals, would find that useful. We did not want to turn the multi-wire into moly. We would have had to pressurize it basically like a little bomb in the house. So we moved in the direction of the CCDs. And the idea was to have a quick data collection for difficult samples. What we had not realized by measuring highly redundant data, we were getting more signal to noise for each reflection. So we got better data for very small samples and for very large unit cells. So I think this was a fortuitous case. We designed something that ended up being better than we thought it was going to be. And the reason I put in this R&D 100 award photo, which was received for SMART, this is the only time you'll ever see Bob Sparks or Jim Fay or Charles Campana in a tuxedo. In the 90s, up to 600 non-hydrogen atoms a week or less per structure, and an astonishing 229,000 structures in the database. Now it's getting difficult for me because there's a lot of things going on in what is just this last decade, so I have a very dense slide here. But CCDs prevalently used in North America, the Bruker line, the Nonius line that then came together and became the Kappa Apex 2, and the Kuma and then Oxford diffraction group coming in. And I'm sorry I don't have photos of those because they were not comfortable of me including them. So I haven't excluded them. I've tried to be sort of once over lightly with all the vendors. But obviously I have access to a lot more photos from our group. Low temp devices, Oxford Cryosystems makes some wonderful machines which we all offer, and some independent machines from both Bruker and MSC and Cryo Industries. Benchtop systems, notably introduced for chemical crystallography in this decade. And microfocus, sealed tube, source and optics become in routine use. And now, a number of choices there. PCs all over the place. The same interesting public packages, and you'll know some familiar names going back to the 70s there, still around. Yana 2000 for modulated structures becomes accessible to all of us, and some nice workshops at ACA for that. And GUIs, very comprehensive GUIs and easy to use, become prevalent. WinGX, the OLX2, nice workshop here at this meeting, and Hubschla's Shellexla right at the end of the decade, and commercial software, in particular from Bruker and Rigaku for structure solution and refinement. And so here's what the machines kind of came into from the CAD4Q automation there, and the SMART line coming into dual source Apex 2 type instruments. And here was the design team, I would say right at the beginning of the decade. And again, a treasured photo of a few people you never see. Here's a young Roger Durst who conceived of both the Apex 1 and Apex 2 designs. And here's Bob Sparks, shortly before, I think, the accident in which he died. And the famous John Chambers, whom none of us have seen for decades, I think, the author of Saint, going back to the multi-wire days and continuing to develop it to this day behind the scenes. So this is John hiding in the back here. And by the end of the decade, 1,000 non-hydrogen atoms reasonable. I remember George solving one, certainly a few years ago. Many twin structures become routinely available, a few hours to overnight for completion of the structure, and over 500,000 structures deposited. And to this day, a few interesting developments even at this meeting. The CMOS systems introduced for home lab use. Pilatus, of course, used at the beam lines for some years, and now some home lab modules. And the CMOS that we introduced last year starting to become in routine use around the world. Increasing use of benchtop systems for quality data, certainly better quality than on the point detector diffractometers that, on which thousands are deposited in the databases, and facilitating teaching. It's so easy to ship a benchtop system like this to workshops and have it easily used in different places to facilitate the instructional information. Even brighter home lab sources, the rotating anode generators and this new liquid gallium metal jet that you can see in the exhibition, and wide use of the microfocus sealed tube sources. And the notable 600,000 structures reached this year in the database. It's a little bit what the microfocus sources look like. Simple sealed tubes, whopping great multi-layer optics coupled in close to deliver a very bright beam on a really low maintenance system. So that makes it interesting. And what has this done for everybody? Here's the CCDC wonderful chart from the latest website, seeing the increase in number of structures over time. What has that given us? Better quality crystal structures, as well as many more crystal structures for routine problems. Now we have software in which crystallographic expertise validation to help with error checking as this ever-increasing number of structures comes along, and report generation are built into programs, giving us capabilities to analyze larger structures, smaller crystals, unstable compounds, twinned multiply specimens, and modulated structures. And as George said yesterday, it is a very interesting time to be around. So, that's the end of the talk. I genuinely want to thank my co-author, Charles Campana. He had the framework of this whole idea at a doll symposium several years ago, and I poached happily on that. And I also thank very much my colleague Frank von Meurs and Dan Frankel, sort of from the Nonius side of collective memory, for the historic Nonius and other diffractometer slides. Frank gave a wonderful talk in Madrid about the history of Nonius, and I poached happily on that. Thanks very much to the colleagues at Rigaku for permission to use their slides, and to Ron Hamlin for supplying me with the Mark I multiwire. Thanks so much to the newsletter editors at IUCR and ACA for always gathering wonderful photos, and I picked up a couple from those for Eric Daves and Fax One. To David Watkin himself for permission to use his photos. To Peter, who takes so many wonderful photos at these meetings. To CCDC for all the work they do, obviously, and the information statistically, and to our own company archives. And to you, thank you so much for giving the opportunity to do this and for listening.
I see a question there already.
I just want to emphasize one thing. There's the programs from Oak Ridge and also Fordab on Sulphur were open source. You would get the source code to innovate, something you can't do anymore. So it was a very important aspect of the early development of computing. People would use it
For the open source so that people would improve and improve on them.
Right.
Yeah, I agree. I agree. And I think we can, however, thank many of the public software developers for at least having the code all out there. And I must say, in the early days, we would argue fiercely with George about having more proprietary software available and less public. And George always insisted that it would be more important to have more people use the software. And he was absolutely right. So I think there's a very good way that the commercial vendors can work with the software developers, and it's been a good model, absolutely. Yes?
I thought it was nice that Jim Stewart used Pigeon Fortran on for his computers.
To make it easy.
So that you could, he used Pigeon Fortran, which was Fortran that was interpreted in the same way by all the current computers of those days. Otherwise, you could get into trouble if you took a program and used it on a different kind of computer.
Yeah, to make it very easy to
And there are all
transport.
kinds of ways to try and make sure things work well for the crystallographers. And he gave his source data.
Yeah. Yeah.
Programming data.